So, let us do step 1, okay, which is FHE encryption to TCF encryption. So, it turns out that there is no generic way as such that you can convert an FHE encryption to a TCF encryption, but using existing schemes from the literature. For instance, the GSW scheme that we have seen of classical FHE, using certain special algebraic properties of those, you can convert the FHE encryption of S to a TCF encryption of S. So, now what was our TCF encryption? It was this trapdoor claw free function pair. So, I need to define an F0 and F1, it needs to satisfy the properties I want. What were the properties? Well, injective, same image, hard to find a claw, but exists a trapdoor which makes it easy. These were my properties. And sorry, there it is an encryption of S. So, I also need that the first bit of the claw XORs to the secret. Okay, these were the properties that I wanted. So, let me outline this transformation. So, I need to define F0 and F1. So, remember that F0 takes some mu 0 r 0 and F1 will take some mu 1 r 1, right. I need to define these. So, F0 is actually easy to define. So, this is just the FHE encryption of bit mu 0 with randomness r 0. So, the FHE encryption algorithm is a function. Okay. What does this function take? It takes a bit, a message bit which it encrypts, and it takes some randomness, right, which it uses to perform the encryption. So, my F0 mu 0 r 0 is just defined as the FHE encryption of bit mu 0 with randomness r 0. Is the definition clear? Now, I will define F1 in a careful way, so that I get this TCF pair which is an encryption of S. Okay. So, how do I define F1? Well, I define it as F0 of mu 1 r 1 XOR and FHE encryption of S. So, now note that S has to somehow come into the picture, right, because I need this TCF encryption to encode the bit S. So, what am I doing? Well, I am doing an encryption of mu 1, F0 is what? It is an FHE encryption. Okay, so, let me write this F0 mu 1 r 1 as simply enc of mu 1. Okay, forget the randomness used in the encryption for a second. So, enc of mu 1 XOR enc of S, right. So, this is by homomorphism enc of mu 1 XOR S, which is what? Yeah, it is just this, right. So, it is enc of mu 1 XOR S. So, now I want to check the properties of the encryption scheme. So, the first thing that I want to say is that if F0 of mu 0 r 0 is equal to F1 of mu 1 r 1. So, if there is a claw mu 0 r 0 and mu 1 r 1 are a claw, then I want to claim that mu 0 XOR mu 1 should be S. I want to claim this, right. So, that it is a TCF encryption. So, what is F1 of mu 1 r 1? We have just seen that this is enc of mu 1 XOR S, right, and the left hand side is just enc of mu 0. Okay, so, this implies that mu 0 is equal to mu 1 XOR S. So, I got the first property. So, let me just write here for clarity, check TCF encryption properties. So, I am just checking these TCF encryption properties. So, well, the very first property better be that it is actually encoding S, right. Now, I also need other properties. So, what are my other properties? It should be claw free. So, that means that it should be hard to find the mu 0 r 0 mu 1 r 1. Who can tell me why that holds? Yeah, go on. Very good. So, it holds by the security of the underlying FHE. Why? Because if I could find a claw, that means I found in particular mu 0 and mu 1, right, and XORing these I will get the secret S. Okay. So, this is claw free by security of FHE. Okay. What are the other properties I wanted? Well, I wanted that the functions should be injective. So, that is okay. I wanted that the image should be the same. This actually is a little bit of a problem, but this can be arranged. I am not going to do it in class, you can look at the paper. Okay, it is a technical, it is a technicality. So, I need the image to be same. It turns out it will not be exactly the same the way that I have defined it, but it is a technicality which can be done. And what was the last thing? I needed a trapdoor, right. So, I should have a trapdoor which lets me find the claw. So, note that the FHE decryption key would not be enough, because I need to recover the whole claw. So, mu and r, right. So, luckily the lattice based FHE schemes that we have, they support trapdoors. Okay. So, we did not do it in this course, but yeah, there are trapdoors of lattices, and these lattice based FHE schemes, I can use that lattice trapdoor to recover the randomness. So, without going into any details, I am just going to say that FHE schemes from lattices or not all I should say, but some FHE schemes support a trapdoor which allows for randomness recovery. Okay. So, the FHE scheme that I use needs to satisfy properties that enable all this, and she calls them quantum capable FHE schemes. Okay. And existing schemes, in particular GSW, we can sort of make it quantum capable. So, this is something which I would have loved to do in class, but we will need to sort of define these trapdoors and so on. We do not have time for that. So, I will leave this at this level of detail. So, using this quantum capable FHE, which can be instantiated from LWE, we can convert our FHE encryption of S to a TCF encryption of S. Using a TCF encryption of S, right, by entangling the state with a superposition of clause, we get something that has a few superfluous terms like mu's and r's, right. We can do a little bit more processing, so some Hadamard and some measurement to get the QOTP that we want. So, this gives us the encrypted C0 functionality that we wanted, where we have A, B, C, right, and we were calling it S, A and B, let me stick with that. So, S, A and B, where we have the control bit S, we have it as an FHE encryption, right, and we want to get as output encryption of S, B and a quantum OTP of B XOR AS. Okay. We reduced that to that is the encrypted C0 thing which we now showed how to do, right, and this we had previously shown was sufficient for encrypted Toffoli computation. Okay. So, obviously there are a lot of missing details, but I believe I have outlined all the main ideas, and for further details I refer you to this really nice paper, and you can read more there. So, this is beautiful stuff, right. I mean, this is the modern research in quantum cryptography. Good. So, let me conclude the sort of the description of quantum FHE here and just say a few final words about everything. So, I am happy that I got to show you at least one advanced primitive even in quantum cryptography, right. And similarly, we saw the same advanced primitive of FHE in classical cryptography, right, in lattice based cryptography. There is more that I had hoped that we could talk about. So, within quantum cryptography as well as within post quantum cryptography, there is a whole host of really interesting and elegant constructions, and more importantly lots and lots of open problems. Okay. So, the party has just begun. There are lots and lots of things to do, and I hope that seeing these different ideas helped to set the stage a little bit and give you some context of both what are the foundations for these ideas as well as a glimpse of how they are used in modern research. Okay. So, let us take a step back and survey what we have seen in the class, right. So, we started by looking at quantum information, how it is fundamentally different from classical information, right, the notion of a qubit and how to sort of operate on these qubits. And we saw some really magical things, right. So, we saw that this quantum Fourier transform, which can be computed efficiently over qubits, allows us to do something very significant in the quantum setting, which we do not know how to do efficiently in the classical setting. So, in that sense, this is a very computing science perspective, right. So, given exponential time you could do something, but here we have a way of exploiting this quantum parallelism to do things that we did not know how to do efficiently in the classical setting. So, we saw a whole bunch of algorithms that showed us the power of this quantum Fourier transform, right. And right, remember, so there was this slogan that we were using, I did not come up with it, it is a standard one. So, this rotate, compute, rotate, right. And we saw how using this rotate, compute, rotate, we can do a lot of sort of surprising things. In the beginning, we saw examples which may have seemed a little contrived, right. So, for instance, the Deutsch-Josa, which is the classic first thing that you see, it may seem like, well, it is more of a contrived example perhaps, which may not be very applicable in the real world, but nevertheless it shows us something very surprising and beautiful, which is that this Fourier transform gives us actually something very substantial, right. So, it is giving us a kind of an exponential speed up, which we saw via various algorithms. And then we saw two very relevant algorithms, very practically relevant algorithms, Grover's algorithm, which gives us a very big speed up on an unstructured search problem, right, which is deeply connected with one-wayness in cryptography. So, by the way, I mean I can tell you that in cryptography, like having even a little bit of improvement in one of these questions is a big thing. So, really Grover's search is giving you a very huge improvement, and it is a big deal for us, right. In particular, it would force you to really expand the key sizes for the same level of security. So, that is really very sort of significant practical impact. And then of course, we saw Shor's algorithm, which is one of the reasons why we take post quantum cryptography very seriously. So, now having broken things like RSA and discrete log, which also we studied in a little bit of detail, right. So, before breaking them, we also saw what we are breaking. So, we saw encryption schemes from RSA and from discrete log. We saw the random oracle model. Unfortunately, we did not have time to see the quantum random oracle model, but I had hoped that we would. Anyway, so we saw these crypto systems which are being used in practice all over the world, right, and we saw that this Shor's algorithm is going to break them. Subsequently, we looked at how to search for problems that do not admit the kind of structure that this particular type of algorithm can exploit. So, here I did spend a lot of time sort of emphasizing, and I will re-emphasize yet again, that we do not actually know that lattices or in fact the other variants of problems, post quantum problems like code based cryptography, isogeny based cryptography, multivariate cryptography, it is all a very rich space. I mean, we do not in this course we do not have time for that, but we do not actually know for sure that these are not going to be vulnerable to quantum attacks. So, in fact, many people think that lattices do have structure that might admit quantum attacks, but currently our state of knowledge of quantum algorithms is such that it seems that we fall outside what power quantum gives us. And this is also something that we did discuss in class, right. So, we abstracted out all the problems that we saw as this HSP hidden subgroup problem, and we saw how the lattice problems are in a non-commutative version of this problem, which we do not really know how to we don't know how to speed up using quantum. Okay, so having seen that, we saw a little bit of a taste of lattice based cryptography. Here we saw encryption, basic encryption again, and of course this wonderful primitive of fully homomorphic encryption, right. And subsequently we switched our attention to trying to use quantum to build cryptography, where we saw once again we saw key agreement, one time paths, public key encryption, and now fully homomorphic encryption. So, it is for me it is a bittersweet type of an experience, because I feel that any one of these topics is so rich and so deep with such amazing structure and so many interesting things that could be studied. Like number theoretic cryptography is beautiful in itself. I mean, so what if it is broken by quantum, right? But we had very little time to look into that. Lattice based cryptography is amazing. We had very little time to look at that. Same for quantum algorithms and same for quantum cryptography. So, I feel like we have just barely tasted a little bit of all of these things, each of which could have multiple courses devoted to them. But I only hope that seeing these all things together gives us a perspective that maybe seeing any one of them in depth would not have. So, that is the reason that we designed the course in this way, and also the classroom is full of students from different backgrounds ranging from CS to EE to EP to physics and so on. So, I hope that there was a little bit in it for everybody, and that all of you will feel excited and encouraged to explore whichever aspect of it is most interesting to you. I hope that you will explore it further, and I hope to see you again in some other class. Thank you.